Group 2 elements. Group 2 elements include beryllium, magnesium, calcium, strontium, barium, and radium. The abundance of calcium and magnesium are high on Earth. The typical physical properties of the alkaline metals, group 2 metals, and their ions are summarized here. We notice that there are 2 valence electrons for each element. The atomic radius increases with the atomic number. So does the ionic radius. The electronegativity values of beryllium and magnesium are higher than that of others. The first ionization energy, IE1, decreases down the group, so does IE2, but IE1 of radium is larger than IE1 of barium, which is attributed to the thermodynamic 6s inert pair effect. We'll talk it later. IE3 is much larger than IE1 or IE2, indicates the difficulty to remove one more electron from the bication. The atomization energy decreases down the group, indicates the interaction between the atoms decreases. The variation of atomization energy leads to the variation of the melting point and the boiling point. In addition, only calcium, strontium, and barium show visible emission in the flame test. Calcium, strontium, and barium exhibit similar chemical behaviors, generally resembling but being slightly less reactive than sodium. But beryllium is special, mostly from covalent compounds. The oxides, except beryllium oxide, react with water. Beryllium oxide dissolves in acidic and basic aqueous solution, forms hydrated beryllium ion. Except beryllium, other alkaline earth metals are not stable enough, react with oxygen, nitrogen, sulfur, and halidon. The difference between the first and the later members of group 2 are also illustrated by the formation of hydride and carbide. The carbide reacts with water. Beryllium carbide reacts with water to give methane, while calcium carbide reacts with water give acetylene. Covalent beryllium difluoride and beryllium dichloride are very soluble in water. Very interesting. It's because of the high enthalpy of hydration of beryllium ion. It's about minus 2,500 kilojoules per mole. The dehydration of hydrated beryllium chloride yields hydroxide, not chloride. See the last equation on the slide? These 2 equations show you that if you try to purify beryllium dichloride solid by recrystallization, after you dissolve beryllium chloride into water and remove the water away, you will never obtain beryllium chloride again. You just get beryllium hydroxide. In the vapor state about 1020 K, beryllium chloride is monomeric and has a linear structure. At lower temperatures, the vapor also contains planar dimers, even polymers. The BeCl bond length is longer than in the monomer. Each beryllium atom can accept 1 or 2 lone pairs of electrons, thereby acting as a Lewis pair of electrons, thereby acting as a Lewis acid. Each chlorine atom in monomeric chloride has 3 lone pairs of electrons. The dimer of beryllium chloride forms by donation of a lone pair of electrons from chlorine to beryllium. The oxides of the group 2 metals, but not beryllium, are usually prepared by thermal decomposition of the corresponding carbonate. The melting point of oxides from group 2 elements decrease down the group, indicates the decrease in lattice energy as the cation size increases. The high melting point of magnesium oxide makes it suitable as a refractory material. All the peroxides, except beryllium, because beryllium peroxide is never prepared, are strong oxidizing agents. The peroxides are thermally decomposable. The stability with respect to the decomposition reaction increases with the size of the metal ion. The thermal stability relates closely to the lattice energies. Lattice energy delta U is very difficult to determine experimentally. It's usually estimated by Kupczynski equation shown on the slide. From the equation, we may notice that delta U is inversely proportional to the sum of the ionic radii. Given that we have the data of ionic radii, then we can estimate the lattice energy of the solid. Beryllium hydroxide is amphoteric, reacts with either acid or base. The hydroxides of the other group 2 metals are all basic. The solubility increases down the group. Beryllium carbonate tends to hydrolyze, giving a salt containing beryllium tetrahydride ion. The carbonates of magnesium and later metals are sparingly soluble in water. The metal carbonates are much more soluble in an aqueous solution of CO2 than in water due to the formation of a bicarbonate ion. See the chemical equation on the slide here. However, salts of bicarbonates have not been isolated. In contrast, solid bicarbonates of group 1 metal and ammonium ions are available